This is the 18th video in a series on single agent search. And in this video, we're going to continue on bidirectional search, which we've been looking at for a few videos. And what I'm going to do here is I'm going to show what happens when we want to assume that we have a consistent heuristic. So we're still going to be looking at front-to-end heuristic search, where we have a goal state and our heuristic is towards the goal, not from between the fronts of the bidirectional search, but we're going to see what happens if we have a consistent heuristic. So this is front to end search with a consistent heuristic. And what's going on in this problem is that we're going to get to add something to what we had before. So if we look in the general case, what we had is we computed a lower bound. So a lower bound of a pair of states u comma v was equal to the maximum of a couple different things. So maximum of the f forward of u, of the f backwards of v, and then of g forward of u plus g backwards of v. And given no additional information, so this is a search that this is the only information I have, then this is the best that I can do. And in this case, we talked about in the last video how the algorithm NBS is able to handle this case. And in this case, it has a guarantee that it does no more than twice the number of node expansions than the minimum possible. But there's been a number of observations over the years about how you can actually do better than this. And these observations haven't been necessarily built on the same theory here. And so what I'm going to do in this video is I'm going to try and reformulate those or show how they're related to this theory, because I think this is an important connection that actually you won't find it in the literature right now. But if I want to add consistency, then let's see what happens. Okay. And if we think about what's going on here, consistency, there's nothing inside the f cost that says anything about consistency or that really matters. There's nothing inside here then. And so the place that I can add consistency is in this g plus g bound. And so now we're going to do this. I'm going to abuse notation here. I'm just going to use LB again, because I'm not really going to be comparing against these. So we're done with the general case here. And now we're going to move to the consistency case. And we'll just use that lower bound for the rest of this video. So lower bound between uv, again, is going to be the maximum of a number of different terms. And the terms are basically going to be the same as before, with one addition. So f forward of u, f backwards of v. And the additional thing that I get now is that I have g forward of u plus g backwards of v. But now I know that the heuristic is consistent. And if the heuristic is consistent, what I can do is I can look at the change in the heuristic. Now remember, with a consistent heuristic, the heuristic can go up sort of an arbitrary amount and it doesn't matter. So what I want to think about is how much could the heuristic go down? And so what I'm going to say here is, well, I've got a heuristic in the forward direction of u. And if I imagine it goes down, if I want to ask, what is the distance between the two frontiers? I'm going to use consistency here. So h forward of u minus h forward of v. And we know that is going to be less than or equal to the distance between u and v. And so what we're doing here is we're getting an estimate of the front-to-front distance between u and v by using the consistency of the heuristic. Okay. And I'm not writing all out the derivation there, but we've seen this enough times, so hopefully this is clear by now. And this is using the heuristic in the forward direction. We can also use it in the backward direction. So g forward of u plus g backwards of v plus h backwards of v minus h backwards of u. So this would be the ideal thing that we could add. And if we were just to add these conditions here directly to our search algorithms that we have, so particularly if we looked at something like NBS, If we just change the lower bound to be this lower bound, then NBS, this is the definition of, this actually gives us the definition of necessary expansions. Any LB, any pair of states with LB less than C star are necessarily expanded. And we could just run this and everything would be great. We could, just directly transfer over everything that we've built in existing algorithms. The problem here is that with a pair of states, then before what we could do is we could sort of filter on F, and then we could look at two states and see if their G costs allowed them to be under the frontier, and then we didn't have to look at the H cost for those states. And now what can happen though is that depending on how I pair my states together, I might actually get H cost estimates that that one pair of states with equal G cost would be something I could expand, and there'd be another pair that maybe would have a lower bound that would be too high. And so the problem here is that this comparison is starting to cause us to do sort of an n squared front-to-front comparison if we're not careful. And so there's a number of algorithms that basically are trying to come up with ways to avoid having to do this sort of arbitrary comparison here. And so what I'm going to do is cover those algorithms and where they come from, what the information they use, how it relates to this general picture of a consistent heuristic, and then we'll connect them all together, and then we'll talk about how you build algorithms for that. And I ran out of space on the side there. But anyway, so we're going to look primarily at the consistency case today. And the general case is just for reference so we can see what the difference is. Okay, so let's start looking at a number of different approaches, and we'll just look at what each of these adds to the picture. So the first thing we're going to look at is epsilon. And epsilon allows us to do slightly better. And what epsilon just basically says is if we have a minimum edge cost, then my term, which before was gf of u plus g backwards of v, I'm now able to add some epsilon to that. It just says, yeah, if all edge costs are 1, then if I am bounded by this g plus g term, I know when I connect the two g's together that the edge that's connecting them has to have at least some cost epsilon, whatever the minimum edge cost is in my state space. Okay, so the next thing we're going to look at is some work by Kindle and Kynes. And this is work back in the 1990s. And in their work, they were assuming a consistent heuristic, and they were looking at some error that existed in the heuristic. And I'm going to describe this work from our perspective of the more recent theory, thinking about going between the frontiers, because I think we'll be able to understand what's going on here a little bit more easily. The idea here is, suppose I have some state, and so we have d of x, and we're going to measure the error for that state. And we can measure the error both in the forward direction or in the backwards direction. So I'm going to say dx of n. This is going to be the measure of error. It's going to be gx of n minus hx of n. And what this means here is this measure of an error is going to be let's say this is the forward frontier. This is the actual distance in the forward frontier minus the backwards heuristic of the same state. So just to draw a picture of that, we can do this in the forward or the backwards frontier. Let's do it in the backwards frontier for a second. I'm going to call this V just because it's going to be consistent with the picture we have in a moment. We have the goal here. And the idea here is we have two estimates of the distance between V and G. We have H forward of V, and we have G backwards of V. And notice here that G backwards is exactly accurate. We've done a backwards search. If we've done it with a consistent heuristic, then we know that when we've expanded this state, or if we're about to expand this state, we know that this is going to be an accurate cost for this state. And H is only going to be an estimate. And so we want to look at this picture now, where I have another state over here, U, which I'm thinking about expanding. And we're going to think about, okay, I have some G cost to get to U. And then I have an estimated heuristic, which I'll draw in red here, of how to get to G. And I'm going to think about, though, what do I know about this heuristic error which exists between V and the goal? I'm going to write this down, and then we'll do the math, and it'll be apparent what's going on here. It may look a little bit funny before we do that. So what we're going to say is, look, if I come to some state, I'm wanting to think about my lower bound. So I'm thinking about a lower bound between u and v. And I'm not going to write all the different pieces out. So I've got all these, the same sort of things we've been seeing up here. And so what I'm going to do is update my f cost estimate. So I'm going to say, look, when I have a state f forward of some state u, that I'm thinking about a pair of states u and v. And if I'm thinking about the path that actually goes through v, then actually I know that there's some error here between what the heuristic says and what the g-cost says. Because if the g-cost is 3 and the heuristic says it's only 1, then I actually know all my heuristics are going to be off by 2 when we're thinking about coming through v. Okay, so let's watch, and therefore here I can compensate for that by adding d in the backwards direction for v, my state, in the opposite direction. Okay, so this is just part of all the other pieces here. But this is the term that I'm going to get coming from Kindle and Kynes if I rewrite this in this lower bound framework going from u to v. Okay, and why is that the case? Well, so we're just going to see what happens here. Let's write this out. So f forward of u is equal to g forward of u plus g backwards of u, and d of b is equal to g, so this is in the backwards direction, so I'm going to get g backwards of v minus h forward of v. Okay, and if we look at what's happening here, oh, sorry, I wrote this, so this is g forward, and sorry, my eraser is a bit too big, I need to make it smaller so I don't erase all of this. Sorry, this is supposed to be h. Wow, okay, so I really said that wrong. So I have my f forward is g forward plus h forward of u. My d is g backwards of v minus h forward of v. And when I take this apart, what I'm going to see is g forward of u plus g backwards of b, and then I get h forward of u minus h forward of v. And actually, if I come up here in this terms, then I have g forward of u, g forward of v, plus h forward of u minus h forward of v. Okay, so this term here, for consistency for the lower bound, this piece right here can be rewritten as f forward of u plus db, this d term, which is the error term in the backwards direction of v. Okay. So this is, and we can see this is just equivalent to assuming consistency. So this term here just says, look, I can take my f and I can take d of b in the backwards direction. Now, what Kindle and Kynes have to do here, because of course this is an expensive calculation, we don't want to think about this in front-to-front terms, all pairs of u and v. So they're going to shortcut this and they're going to say, well, instead of using db of some state v, we're just going to think about the minimum. Okay, so in practice, what they're actually saying here is we'll use f forward of u. We want to get rid of the v in this statement, so we're going to say plus d min in the backwards direction. Okay. And this is basically saying this is an improved estimate of states that are necessarily expanded when we want to prove our solution quality. Okay, so we can, in practice, what we really want to use is we really want to use this term up here. This term up here is giving us what we get exactly from consistency, but we can't necessarily think about both. We don't want to think about both u and v. And so they said, well, we're going to take our f cost and we're going to add, well, we'll add the minimum to it. And so this is an estimate of taking, for any pair of states, actually just getting this calculation right here. But so we can now take our f cost, we can add the minimum error for any state in the backwards direction, and you can do the same thing, f of backwards of v plus d min in the forward direction, and that's going to give us a better estimate for the terms here that are part of our lower bound calculation. Okay, so that's our d value, and that is Kindle and Kynes and their work on top of that. So that's a nice estimate. And there's another estimate that was that came out a couple of years ago, about 5 years ago, by a researcher in India. Yeah, so there's a paper by Alcazar, by Mike Barley, and Pat Riddle. And so I'll put this in here. This is the paper that is a recent paper from AAAI 2020. And it is helped put together some of these bounds. Again, they didn't do it in the front-to-front way, but they did put these bounds and notice that there's some connection between the bounds that were being looked at here. And you'll find the link to the work that our next bound comes from there. Okay, and so what we're going to get is this next estimate, and we're going to call this a bidirectional estimate. And here we go, estimate. And so the kinds here is a D error. And I'll come back to this term. And here we're going to get a bidirectional error, which is going to give us an estimate, which is B of x of some state n is going to be f of x of n plus d of x of n. Okay, and what's going on here is, in a similar way, if we go back to the kinds, the d term here only depends on one node. It doesn't depend on a pair of nodes. This is another estimate that we can get that is only going to depend on one node, and it's not going to depend on a pair of nodes. And so this is something that is, what we're going to show is that, again, it's equivalent to what's being done up here, or what the ideal of what we're trying to do up here, but it is, it's done in a way that can be computationally a little bit more efficient. And so the idea here, if we think about, what is going on here? This is a little bit weird, because if we look at our picture in this bidirectional estimate, sorry, the S is bothering me there. Okay, so if we think about our start state here, we think about if we're going in the forward direction, then we have some state n here. And what we're thinking about is like the F cost, which is basically this path estimate through here. And then we're thinking about the error that actually exists in this portion if we were to be doing a backwards search. And what's going on here is the idea of this bidirectional estimate. It's saying, well, look, this piece of forward search here is always going to be connected with some backwards search. And that backwards search, whatever it happens to be, is going to get this part wrong. And so what we're going to do is we're going to just put this directly into a bidirectional estimate of the forward cost plus the error that the other direction of search is going to get when we actually do that piece of search. And the idea here is that we're going to make a bound. So I'm going to turn this into, again, a UV bound. We're going to say a bound of U comma V is equal to B in the forward direction of U plus B in the backwards direction of V. And so if you think about this piece, okay, so just to say, because this is the same node and it's always in the same direction, then this is something that can be calculated in one frontier. We can calculate the minimum as an estimate, but this is basically something we can calculate efficiently. When we think front to front, though, I think about this is an estimate of the full path length. This is an estimate of the error in the other direction. So I can go here and say, well, I'm going to take two of these estimates from a state U and a V, and I'm going to add them together. Now, this is a full path estimate, as is this. So that means I'm actually getting twice the path length. So I need to divide it by 2 if I want this to be an estimate of actual path length. And so let's take a look at what's going on here. So B in the forward direction is going to be F in the forward direction of U plus D in the forward direction of U. And then here I'm going to get F in the backwards direction of V plus F in the backwards direction, D in the backwards direction. D in the backwards direction of V. And I'm going to expand this all out. You might be able to guess where this is going. But here we're going to get G in the forward direction of U plus H in the forward direction of U And then what is D in the forward direction? Well, D in the forward direction right here is G in the forward minus H in the backwards. So this is going to be G in the forward direction of U again, minus H in the backwards direction of U. And then I'm going to get the same thing continuing here. So F in the backwards direction is going to be G in the backwards direction of V plus H in the backwards direction of V plus G in the backwards direction of V minus H in the forward of V. And if I look at what's going on here, and actually I'll go ahead and highlight these. So we have two pieces here. Actually, what we see here is G in the forward appears twice. G in the backwards appears twice. And then what do we have here? What we actually have is H in the forward of U minus H in the backwards of U, and then H in the backwards of U minus H in the, did I write one of these down backwards? Oh, forward, backwards, backwards, that's forward. Let's look at this again. So G in the forward of U twice, G in the backwards of V twice. That's V. Oh yeah, so then I have G in the backwards of V and G minus, sorry, H in the backwards of V minus H in the forward of V, which going up here is this estimate, H backwards minus, H backwards V minus H backwards of U. So right, this is H backwards of V minus H backwards of U, and then I have H forward of U minus H backwards of U. So that takes care of these pieces. So what this is equivalent to is it really is equivalent to adding both of these up and dividing them by 2. So adding both of these equations up, divide them by 2. And what that captures is it captures the error in both directions simultaneously. But because we've captured both of them, we have to divide it by 2 because I can't actually capture that twice. So what we can see is this bidirectional estimate here, just thinking about that piece, the bidirectional estimate, if I think of it as being a front-to-front estimate, is again, it's just 2 estimates. It's combining together 2 estimates of, it's combining together the 2 estimates that I was wanting to have here and giving me an estimate of that. But because it's based on a calculation here, which only uses 1 frontier at a time, we can actually calculate this more efficiently. And so, so this would be the 2 frontier version, but the single frontier version looks something like this. Okay, so if we try and put this all together, and we're trying to think about like what are our algorithms going to be, or what are they going to do, then if we think about our necessary expansions, I'm going to have to expand states until, as long as there's states that meet a number of conditions. And basically they have to be less than the lower bound. And so my conditions are going to be thinking about overall, I have, so going here, if I'm thinking about expanding a state, we can convert all of these into general estimates of what the optimal solution is. Okay, so in general, we have, well, I can take F min in the forward direction plus D min in the backwards direction. And this is an estimate of the optimal solution cost. We also have F min in the backwards direction and D min in the forward direction. Okay, D min, as I said before, is just looking at this D calculation right here. And it's saying, you know, what is the minimum value across the frontier? Because over all my values, I can add the minimum to every other F cost. So I get the minimum and I can add it to this F cost. I can also get here B min in the forward direction and B min in the backwards direction divided by 2. And then I can also get G min in the forward direction and G min in the backwards direction plus epsilon, whatever it's going to take to connect these states. So this is all of these together are giving me an estimate of C star. Okay, these are all an estimate of what the optimal solution cost might be. And all of these are giving me a chance to raise up my estimate of C star. And so as I do this for particular states, then I have to expand, of course, all states that are underneath that, for pairs of states that are underneath that estimate. But we can basically, we can expand these states to try and build algorithms. So if I want to describe algorithms, and so what we see here is these are a D estimate, and this is a B estimate. Then we're going to have a couple different algorithms. So we have BAE star, and this is just going to use the B bound. So what we're going to do is we're going to basically say, look, we want to keep track of the C star. We have to expand states that are less than that. We, of course, can exclude states. If I have a state that is greater than this estimate that I have, then I can say I don't have to expand that state right now. And in particular, when I think about a particular state, I have an exact F min, and these things like D min in the other direction can be computed efficiently. B min in each direction can be computed efficiently. G min in the backwards direction. So I can take, for any given state, I can use these estimates, and then I can use those along with a single state in the other direction to make it much less expensive to actually do the search. So BAE star takes states, compares them, or adds the B bounds to them, and it searches using those. There's an algorithm DBS, which uses the D bound. So that's the error bound that's coming, that's this one. And then there's DBBS, which is using the D and the B bound. And the only issue here is that there is cost to maintain all of these estimates. And so when you try to search with these estimates, then you're going to have to pay some cost for maintaining those. But generally speaking, if you can maintain that cost, then we can search much more efficiently because we're able to use front-to-front information.